Dr. Nat here. So we are doing molar specific heat for gases, part who knows, but this is still part of chapter 15. So we have seen this word before, specific heat. We have seen this in chapter 14 and we used it in this equation, Q equals to mc delta T, where delta T is the change in temperature, C is the specific heat capacity, and m is your mass. C denotes the amount of heat needed to raise the temperature of 1 kilogram of substance by 1 degree Celsius, right?
Mommy,
We also have
this one,
specific heat
this one,
for gases and we call
this
it
one.
molar specific heat.
I
For gases, we can use this equation. Let's use blue. Oh, blue is already there. So Q equals to NC delta T. So delta T can be in Kelvin or in Celsius. If you have done the web assign for chapter 14, you will know that delta T for Kelvin is equal to the delta T of Celsius, but not for Fahrenheit. Okay, it's not equal to delta T of Fahrenheit. However, T of K is not equal to T of C, so only the change in Kelvin is equal to the change in Celsius. Okay, so back to this equation. So Q equals to NC delta T. For gases, we have two C's, which is NCV delta T. This is when the volume is constant. And another one would be, okay, Q equals to NCP delta T. And you guessed it, this is when the pressure is constant. Okay, so what is N? N is the number of moles of the gas. CV, CP delta T can be either in Kelvin or either in Celsius, but I would suggest you to keep everything in Kelvin so that you don't get confused when you are not using delta T. Alright. Okay, so what is CV and what is CP? What are the units? We're going to talk about it in the next slide. Okay, so recall that we have learned the equation for internal energy of a gas. Whoopsie. Which is U equals to 3 over 2 nRT. This equation can also be rewritten as the change in internal energy equals to 3 over 2 nR delta T. To generalize this equation, the change in internal energy can also be written as delta U equals to NCV delta T. Okay, where CV for a monoatomic gas is equal to 3 over 2 R. Now, what is the CV for a diatomic gas? The CV for a diatomic gas is 5 over 2 R. And for a polyatomic gas, the CV is equal to 7 over 2 R. Now, I can use this equation, delta U equals to NCV, no problem for diatomic, as long as I know that CV is equal to 5 over 2 R. And again, for this guy, it's the same case, NCV delta T, as long as I know that my CV should be 7 over 2 R. Okay? So this makes my equation over here, delta U equals to 5 over 2 nRT, delta U 7 over 2 nRT, and this guy becomes 5, sorry, this is 7. Okay, and this is 5 over 2 nRT. This looks all complicated, so how can you simplify this? You only need to know one equation, which is this guy. You can apply this equation for mono, diatomic, and poly, but you have to know what the CV is. Okay, so this is CV. What about CP? Okay, let me rub this off. So what about Cp, the specific heat, the molar specific heat for gas at constant pressure? So Cp is actually, for a monatomic gas, the Cp is actually 5/2R. For a diatomic, it's actually 7/2R. And for a polyatomic gas, it's 9/2R. In your textbook, you will see that Cp is actually equal to Cv plus R. The question is, can delta U become NCp delta T? The answer is no. Delta U and Cp delta T. The answer is no. Delta U equation is only related to Cv at all time. Okay, so Cv and Cp are just approximation. I forgot to mention that to you. Cp and Cv are just approximations to the actual value of the molar specific heat of the different types of gases. But how accurate is this approximation? We can see that I would say that the approximation is pretty close. If your question does not give you the values of Cv and Cp, then you can approximate by using the Cv equation or the Cp equation, which is 3/2R, 5/2R, etc. Okay, so let's take a look on neon gas. The Cv is 12.7 and the Cp is 20.8. So let's see how accurate it is. So neon gas is a monoatomic gas, so the Cv should be 3/2 times R. 3/2 R is 8.314 joules per mole K. So that is that. So using my calculator, I will get 12.47 joules per mole K, which is pretty close, right? This is 12.7, which is alright. I guess it's off by a few decimal places. And then what about the Cp? Cp is, we have to use 5/2R for a monatomic gas. So this becomes 5/2, this is Cv, and this is Cp. Okay, Cp. So that's 8.314. So 8.314 times 5 divided by 2 will give me 20.79, which is quite close. Yep. If you were to approximate for a polyatomic gas, you would see that the difference between the approximation to the actual value will become more apparent. Okay, so with the increase in number of atoms, the approximation becomes less accurate. So when do we use Cp? When do we use Cv? And how does it tie to everything that we have learned so far? Okay, so we have learned about the first law of thermodynamics, which is delta U equals to Q plus W. Q is heat energy, W is work done on the system. So we have Q over here, we have W, and let's say this is delta U. We have 4 thermal processes. The first one is isobaric. This is what we started with. Isobaric is number 1. Isovolumetric, isothermal, and adiabatic, right? And we have learned that isobaric means the change in pressure is constant. Isovolumetric, the change in volume is constant. Isothermal, the change in temperature is constant. Adiabatic means that Q is equal to 0, which means that no heat energy is absorbed or released by the gas system. So the Q for isobaric is Q equals to NCp delta T. So this is the equation that we should use for an isobaric process. The Q is equal to NCp delta T. So the work done for an isobaric process where the P is constant, W is equal to P delta V. And delta U is just NCV delta t. Even though we used q equals to ncp delta t, our delta u equation still uses ncv. Okay? So let me use a different color. This is like really hard to see, so let's use black. For isovolumetric, the change in V is constant, which means that our W is equal to 0. P delta V, this guy becomes a 0. W equals to 0. What about the Q? The Q, we can say that the Q is equal to NCV delta T. And what about the delta U? The delta U can be NCV delta T. For the equation delta U, Q plus W, W is equal to a 0, so delta U is just Q, right? Delta U is just Q, or NCV delta T. Cool. And remember, isothermal is delta T equals to 0. We know that delta U is related to delta T, so your delta U is actually 0. When delta U is 0, this equation is equal to Q plus W, which means that Q is equal to minus W and W equals to minus Q, whichever you want to use that. Okay, so minus W equals to Q. And there's another equation for isothermal, which is W equals, oh, this is Q. W equals to nRT natural log V final over V initial. It is a positive if we are talking about the work done on the environment, but for our syllabus we are talking about the work done on the gas system, so this becomes a negative sign. And for adiabatic, the Q is equal to 0, which means that delta U is equal to work, and delta U is always equal to NCV delta T. Okay, and work is just work. Okay, or you can use this equation because delta U is work. Aha, there is something that I did wrong, which is I forgot to include the negative sign in the W equals to minus P delta V. This guy, oh my god, don't forget this one, okay guys? Okay, so that is it for this part. I will see you in the next part, or if I decide to make exercises. Otherwise, take care and stay safe. Bye-bye.